Good stuff. Yeah. So I think one of the safest bets, especially if you have an interest in sort of machine learning, or sorry, artificial intelligence, as you spoke last time, you could perhaps, with the research that you have undertaken, you could perhaps ask a question that's kind of relevant to maybe some research that one of the interviewers may be doing that's in line with your interest already, sort of what you've looked at, and maybe something that you're quite interested to know what's actually happening in terms of research and in industry within that capacity. Maybe that's a kind of safe bet type of question. Did you have any other thoughts yourself?
Oh yeah, so another question I asked was, so for the interview, would it be the year 12 content or the year 12 material, or is it year 13 material as well?
Good point. It will most likely be elements of year 12 and year 13, especially at the point where they do try and, if you like, increase the level of challenge. Then it's going to very much delve into the year 13 type material. So it's worth being confident on your year 12 material. But of course, if they do realize that you're finding some of the year 13 material challenging, it's not necessarily going to work against you, especially if you work with the hints, because they will see where you find some of the concepts a bit tricky. They will kind of guide you as best as they can. And I think the key thing there is to try and use their hints, but also, of course, not to try and be quiet while you're processing or at least trying to work through the problem. So try and be as vocal as you can, just at least to give them a glimpse to how you're thinking about the problem.
Yeah.
Yeah. Okay.
That's
Good
fine.
stuff. All right. So it's well, it's really around the corner, isn't it? It's Monday. What time exactly on Monday?
9 o'clock in the morning.
No. Oh, right. So it's the first thing in the morning. Right.
Yeah.
Okay. So you definitely want to make sure you've had enough rest and, of course, get up in enough time so that, you have a moment to just calm the nerves. Okay.
Yeah.
And another thing, Alfie, sometimes, well, what may happen, and it can be quite disconcerting, especially because of the nature of the interview, is that you may find that you are cut short in your sentences, midway through you explaining something. Somebody might say, okay, yeah, that's enough. Yeah, now that can sometimes, and also you may have the interviewers are quite hard to read in terms of the emotions, if you like, so you're not quite sure whether you're going the right way or the wrong way. That again may happen. Don't let that make you lose your composure, because sometimes, you may have a particular idea of how you think the interview might run, and then you find that you're not quite getting the same cues you thought you would be getting on the interview. So I think the point about that is to, of course, like I said, if unsure, try and pause for a moment. There's no harm in pausing. But if they say, yep, that's enough, we have to move on, don't let that kind of make you think, oh, I think they're not happy with my response. That's the reason why they've kind of cut me short. Okay. Sometimes it may actually mean they have identified what exactly they wanted to see you demonstrate, and you've demonstrated it, and they're happy, and they now want to assess your other abilities.
Okay.
Okay. Good
Yes,
stuff.
thank you.
All right, so this idea of curve sketching, of course, and again with the curve sketching, if ever they are to give you questions such as, sketch the curve of x to the power of sine x, that's not going to be the first question they'll get into. I want to assure you, they will build you up to such a question. So they want to make sure that your basics are there. So they'll start off with a question just to warm you up and feel like, okay, right, we can see what his strengths are, and then they might bring in an additional layer of challenge, so to speak. Okay, so just go in there with that mindset that you're not going to be flung into the deep end from the word go. All right.
Yeah, thank you.
Okay, most welcome. Good stuff. Right. So curve sketching then. So how I thought best to probably run this session, given the fact that time is not particularly on our side, is there's no better way of learning than actually you doing it. So there's no point in me kind of using this hour to do a lot of explaining, but more for you to be given scenarios where you can have a look to see how well you've honed your skills on graph sketching, and where there are gaps. Then we can start, of course, looking at ways of how we can consolidate your understanding in that area. How does that sound?
Yeah, that's good.
Okay, good stuff. Right, okay, so just a bit of a title here. So in terms of maybe just using the first part, I'll kind of just run through some of the main things that you probably want to be, or you may well be aware of when you are sketching graphs. So of course, one of the things is firstly, importantly, in understanding that when we have functions, we can either have an even function, yeah, we can have an odd function, and at times we can have a function that is neither even nor odd. So what do we mean by an even function? Any idea what we mean by an even function?
I'm not too sure. I might be familiar with it, but we've not had this terminology in our school.
Yeah, not to worry. So I want to talk about an even function. It's a function really that is symmetrical about the y-axis, okay? So one way to think about it is that if you input a value of minus x, you get the same value as inputting the value of x in there. And a common even function that you have encountered, for instance, is the common parabola. Yeah, where you've got y equals x squared. So you can see it is reflected about the y-axis. Can you think of another even function?
Would one be cos x?
Absolutely spot on. So y equals cos x is another example of an even function, okay? Another key aspect here is an odd function. And another way to look at an even function is, if you have to express it in this way, is that the minus really is swallowed up in the function, so you have the same thing really. But with an odd function, if you input a minus x, then well, the y values are negated. In other words, it's reflected, okay? And you can think about it as having symmetry. So if you rotate an even function in a half revolution, you end up with the same function. So a classic odd function is one that you would have come across, and that is your x cubed graph. So you can see if you rotate this through half a revolution, you end up with the same thing. Another way as well of identifying even or an odd function is you look at the highest power to which x has been raised. So if it is an odd number, then you're looking at an odd function. And if it is an even number, then you're looking at an even function. So anything to the 4, a quartic, to the 6, all those would be even functions. Anything with an odd number here would make that an odd function. But of course, there are some functions that are neither even nor odd. So maybe if you had something, just to give an example here, maybe like y equals x cubed minus x squared minus 5 or something like that. If you use the same conditions, you find that they don't exactly apply, in which case such a function is neither even nor odd. Okay. But in helping us identify whether a function is even, sometimes it can give us an advantage in terms of sketching it, especially if we can realize a symmetry to say, well, it'll be symmetrical, for example, in the y-axis. Then we'd only be concerned at looking at what the shape would be for values greater than 0. So far, so good. Yeah, okay.
Yeah.
The other thing we look at as well is, of course, when given a function and we have to we have to sketch the curve, we think about this idea of the domain. Now, are you familiar with that word domain?
No.
Okay, so a domain is essentially just the inputs that you put into your value. So which values would make or give you a valid y output, so to speak. Okay, so for example, just to give an example here, say we had a function that was y equals root of, let's say, 4 minus x. Okay, so that's the function you're trying to sketch there. And to be specific, maybe if we made just for one positive value here, so just for y equals plus root 4 minus x. Well, in this case, what would our domain have to be? We know that this term this over term in our square root here cannot be less than 0. That makes sense? Yeah, because you can't find the negative, or you can if you're using complex numbers. But in this case, of course, when sketching these curves, you would not have to deploy the use of complex numbers. So in which case, then solving this tells me that all the inputs of x must be greater than 4, if that makes sense. Yeah.
Yeah.
So or greater than or equal to, sorry, greater than or equal to, if you wish, so to speak, must be greater than or equal to 4. So this here now defines the domain. So if I'm to plot this, I know that the values I'll be thinking of for x have to be greater than or equal to 4. I will not concern myself with negative values. Then, of course, the next idea is the range, which is closely interlinked to the domain. So the range essentially is the output or the values of y you get for the corresponding values you use as your domain. So in this case, for example, we can see that the least value of y that we would get would be 0. Yeah, but the greatest value of y, well, x is greater than 4, so the values would, if you like, be positive but greater than 0. So the range for y in this case would be y would be greater than or equal to 0. So if I sort of thought about this as a sketch, then it would look something like this. Okay, where that would be my point 4. So that's, if you like, my y there and my x. And whatever these values are on my y-axis, this would correspond to, just representing this using a graph, that would be my range. And down here then, to whatever point, these values here would make up my domain. Oops. So far, so good?
Yeah.
Good. The other thing as well that we try and do to make our life easier when sketching graphs is we try and identify, well, where does it cross with the y and x axis? So crossing with y and x axis. Okay, and to work that out, what we simply do, of course, you'll be familiar with this, is we set x equals to 0 and try and work out what value our y is. Okay, and that gives us our y-intercept. And of course, rightly so to speak, to get our x-intercept, we set y equals to 0, which gives us our x-intercept. Okay, so far so good. The other thing we look at as well is we look at the limit of our function y as x tends to plus infinity, and also looking at our limits as x tends to minus infinity. So these are almost kind of some of the steps you would go through here as you are working this out. The next thing we would look at then, we might look at something like trying to find the roots of the equation, yeah, which is what we did here by setting x to 0, but that's done anyway at this stage. But the other thing we might want to look at is we might want to identify stationary points. Now, what might we do to identify stationary points?
Differentiate.
Yeah, absolutely. Yeah, absolutely right. So differentiate and set to 0 to locate stationary points. Good. And what else might we want to do that you may have already encountered in your Core 1 maths?
So are we still talking about stationary points? So
yeah. So in this case, for example, if we look at the x squared, of course, we've got a stationary point located here. But what about in this case?
It's point of inflection.
Correct. And so it would have to identify points of inflection. So how would we identify the points of inflection?
Differentiate take the second derivative and
yeah, you're absolutely right. So another thing that we sometimes generally tend to do is that we look at the function and try and take the second derivative and set to 0 to work out what the inflection points are. Now we can then, of course, having had obtained the first differential and second differential equation, we can then, of course, proceed to try and work out where the function is increasing or decreasing. And is that something you've done in your core maths already?
Yeah.
Good. Okay. And then, of course, identify regions where function is increasing or decreasing. Okay, good. So these are some of the kind of key things that you go through. And of course, every problem will have, perhaps you would say, different tricks and different ways you could approach them. But if you generally go in with almost this little checklist in your head, then it gives you a bit of a starting point. And because like you told me already, you've had some experience in curve sketching, and I think the key issue here is maybe trying to look at a variety of different types that you probably could be asked, or anything that at least will give you the key skills needed should you be given something that's very, very novel. So with that said, any questions on the first part so far?
So is the domain the set of values that X can be, or?
Yes, absolutely. It's the set of values that X can be. Yeah. So these are the inputs, because as you rightly know, when we're dealing with functions, we're really thinking about it as having a black box here where our X goes in as our input and out comes our function of X or our Y, so to speak. Okay. So all the values that this X can take, that will produce an output, those we call part of the domain.
Right.
Okay.
So if X is, say, 5, wouldn't be that, because you've written 4 is X is greater than or equal to 4. So if X is 5, wouldn't you get root to the negative 1?
Sorry. My bad. I've had a long day.
Oh, that's fine. That's fine.
I beg your pardon. This is what I meant to say. Yeah. Okay.
Yeah. Okay. Thank you.
Yeah. There we go. Okay. So in this case, then X would have to take on numbers, not greater than 4, beg your pardon, but less than. Okay.
Yeah.
So far, so good.
Yeah.
Excellent. Good stuff. Right. So with that said, then, how do you approach something like this? Just waiting for that to load. Now, of course, here, I think I'm in a position where I can share my Zoom whiteboard. So if you wanted to do that, or you don't have a visualizer, do you, that can allow me to see your, say, work on a piece of paper?
I have my camera.
Okay. Ideally, let's just see how we get on with. So if I stop sharing this,
yeah,
and then I go to a whiteboard, and let's see, maybe that might give us some kind of paper. Or I think you would have to share your whiteboard as opposed to me doing it. Does that make sense, Alfie?
On Zoom, is it? Oh,
yeah. So if you go to Zoom and you go on to share.
Yeah. Whiteboard.
Yeah.
Yeah.
There we go. So I can see it. So the function we're looking at is y is equal to natural log of x over x. Good. Okay. And our domain is for all inputs where x is greater than 0. Okay.
Yeah.
So how might we go about sketching something like that? How might you approach that?
Could you sketch y equals 1 over x, then y equals the natural log of x? Or
yeah, you could start off that way.
So 1 over x would be something like that.
Yeah, good.
We've not done natural logs, we've done normal logs, and it's would it be something like that?
Very good. And how did you deduce that?
I just remembered that log n was something like that because log 10 to the base would just increase as x increases.
Okay, good. Now, another way to think about it as well is that, so you've already encountered Euler's number, so you've worked with exponentials, yeah? So the natural log of x, or the inverse of a natural log, is the exponential. Now, natural log of x is the inverse of e to the power of x, which means, therefore, that natural log of x will be a reflection of e to the power of x in the line y equals to x.
Okay.
So all inverses are a reflection in the line y equals to x. Good?
Yeah, so if it was log, so every log n is just a reflection, right? Okay.
Correct.
Mm.
In the line y equals to x.
Yeah. Okay. So then would you look at some way to combine these?
So of course, in the second or in the first sketch that you have, because x is greater than 0, we would discard the bottom or would not be concerned with the other part in the third quadrant, if you like. Good?
Yeah.
Now, just to give you a bit of a guide here, try and think about where, firstly, that function would cut the y-axis and the x-axis. That's always a good starting point. And once you've got that, then you now start thinking, well, what's going to be happening between these points?
Right. Okay. So to get the y-intercept, we would, we would have put x equal to 0 because we're looking at values of x greater than 0. Would it cross at the x-axis here because it would be 0 divided by this point?
So so which one? So you've decided, so you've made y equals to 0.
Yeah.
Yes, if you make y equals to 0 in that equation, what does that simplify to?
Then it would be so if we put y equal to 0, it would be
Good.
Natural log of x over x.
Good.
Could you times them both by x?
Very good.
So it would be 0 equals natural log of x.
Well done.
And then it would be so that's the same as log of e to the x.
Good.
Equals 0. So then x would be e to the power of 0, which would be x is 1.
Very good. So now you've got the intercept of where it cuts the x-axis.
Yeah.
Very good.
And then
now you might want to find, what about the stationary points?
So we said we would take the derivative or differentiate. Okay. So how would you differentiate a log? We've not done it in school yet. That's
Okay, so not to worry, I can give you what the result is just to make your life easy. So
okay.
the differential or dy dx of natural log of x is 1 over x. So that result I'll give you.
Okay.
So that is dy dx of the natural log of x.
Okay, so
but remember though that in this case you've got you've got a quotient. So have you encountered the quotient rule?
no, we've not done that yet. No.
Okay, so you've not done the quotient rule. Okay, so the quotient rule is a way of differentiating when you have a function divided by another function. Okay.
Right. Okay.
So what I might do is just run you through that, because some of the functions or most of the functions will require that you have a bit of an understanding of how to. I think you may have done it in your C2, your core maths 2 in year
Yeah.
12. I've got a feeling you probably would have done it.
We've not moved on to the core 2 yet because well, because we were online.
Okay. Shall I just shall I show you then if I just go to my screen? Yeah. And then you can have a look and see what it all entails. So you've got a bit of an idea then. Right. If I go over here. All right, you can see my screen, okay?
Yeah.
Okay, great stuff. So where is it? Where's my pen? There we go. I'll use a different color. So if you have two functions, such as these are both functions in x, okay? And I'm going to say y is in the form of two functions of x. To find dy by dx, the quotient rule tells you to say, firstly, you need to square the bottom part, okay, of that function that's at the bottom, okay? And then you multiply u to dv of dx minus v du of dx. Does that make sense so far?
Yeah, I think so.
Okay, good. So if we wanted to find dy dx, and we know that dy dx of ln x or natural log of x is 1 over x, so at least we know this result. So I can call this my u, and I can call this my v. Yeah. So if I square the bottom, I get x squared. So now I'm finding dy dx of this function here.
Okay, so then it would be, so the natural log of x is u. So then it would be natural log of x times t.
Right, my
1.
This is going to be, sorry, this, I normally get it from straight, the data sheet gives you this, so you don't have to memorize this form.
Right, okay.
It should be u. It's easily v du by dx, and this is dv. There we go. Okay. v du by dx. Okay. So yeah, let's have a go again. So x squared.
Sorry, I'll just make it. So it's v dv over x, is it?
V du by dx, and the second term is u dv by dx.
U dv by dx, okay, over v squared.
Correct. But this
Okay.
will be given in your data sheet. You're not expected to memorize this. So even if you can't remember and you say, oh, can you just remind me of the quotient rule? They will give you this. Okay. Likewise, in
Okay.
the exams, you'll be given this. Good. So let's have a go then at trying to work the differential of this.
Okay, so then, v is, so then it would be x times 1 over x.
Good man.
Take away natural log of x
Good.
times, so it's d, so would it just be 1?
Correct. So 1 times, if you like. Okay.
Yeah, so that's over x squared. Yeah.
Good. So now we have differentiated this function here. So dy dx is 1 minus natural log of x over x squared.
So then
Okay.
do we just set that to 0 to find
Correct.
it? Okay.
Okay.
So
with that term, I shall then allow you to share your screen again.
right. Okay. So right. Okay. So okay. Right. So we've got 1 take over x squared
Good.
equals 0. So then we could times both the sides by x squared to get 1 take equals 0. And then 1 equals x. And then that would be, x would be e.
Good. Very good.
Okay.
So that's the turning point. What would the value of y be? So you can get the coordinates of the turning point, or rather the stationary point, if you like, or the turning point.
So it would be natural log of e over e, which is 1 over e.
Well done.
Okay.
Okay, so now we've got another coordinate set, haven't we?
Yeah.
We've now got another coordinate set we can plot on our graph.
So we've got 1, and then we've got e. It is e approximately 2 point something.
Very good.
So I'll say e 1 over e, which is somewhere here.
Yeah.
Yes. Yeah. Okay. And then would it just?
But hang on, you've kind of swapped them a little bit, I think. So
Okay.
the coordinate, the x coordinate is e, and the y coordinate is 1 over.
Oh yes.
Yep. Good.
Yeah. So it would. So that's e, and then
Very good.
that would be 1 over e. So it would
Good
be
stuff.
there.
Good. Okay.
Okay.
So
And
now
then,
you've got a rough idea what's going to be taking place now.
yeah.
Okay, because you've got 2 points now. And then now you've got to ask yourself, now remember what we spoke about, the limits. So as x tends to positive infinity, what does y tend to? If you look at that function, natural log of x over x, as x tends to infinity, what does y tend to?
So if I say it's is it 1? No. Uh, sorry.
Yeah, not to worry, but you can think about it. So x will be a very large number, that x term at the bottom, and that
Yeah.
natural log of x will not be as big as it because you're natural logging it. So essentially y will become a very small number, won't it?
Yeah.
Yeah, so it will tend towards 0.
Right.
So we know that as x becomes very large, the y values start becoming really small.
Okay.
Yeah,
Yeah.
so far so good.
Yeah.
Yeah, very good. And then the other thing we can think about is, well, what about as x tends towards 0? What happens to the y as x tends towards 0?
So as x tends towards 0, so it would be natural log of 0
Yeah,
over 0. So so log, oh, so then it would be log 0, which is weird. So
yeah. Well, actually, you won't be able to determine that that's indeterminate because now you're dividing by 0, isn't it?
yeah.
So that will make it indeterminate. So therefore, this is telling you that we can't divide by 0. Therefore, the line x equals to 0 must be an asymptote.
Okay.
Does that make sense?
Yeah.
Because you can't have x is 0. So x 0 is an asymptote. So you know this curve does not touch the y-axis. And likewise, we have already deduced that it does not touch the x-axis. Yeah, as x becomes bigger, y tends towards 0, but doesn't quite touch the x-axis. Very good.
Okay.
Now, what value will it tend towards? Now, if you try and use your calculator and try typing, I don't know, the natural log of 0.2, yeah, what do you get?
Negative 1.6.
Good, so you get a negative number. So as x
Right.
becomes really small and tends towards 0, we start tending towards bigger negative values of y, because the top term,
okay.
the top term becomes negative.
Okay.
Does that make sense?
So oh yeah.
Yeah,
Yeah.
good. So in which case, how might you then finish off your graph if you thought about completing it then?
So 0.2, if we say is there, then 1.6 would be if we say it's there, and then
Very good. There you go. You've just given me a general shape.
so would then be, would it go down and form an
Yeah,
asymptote?
correct. Absolutely correct. But it would not touch the x-axis, and it would not touch the y-axis because that's the line x equals to 0, and you cannot divide by 0. So again, it will then tend towards increasing values of y in a negative sense, but decreasing values of x. Okay, so far so good. Excellent. All right, so if we go back to my screen share here, well done. So at least you've kind of worked through, you're getting to apply some of those principles in terms of what happens when it goes to infinity and such. And I think the key thing here as well, very important to remember that you cannot divide by 0. Therefore, if you end up with something like this, generally what it's trying to tell you is that the y-axis must be an asymptote. In other words, x equals to 0, that equation is an asymptote. Okay, all right. So I will just go back to my screen here. Okay, so oops, let's go to here. So we've just said this will look something like this. Yeah, and we know that minimum there, that's E, 1E, and we said that would be 1, 0. So far, so good, right?
Yeah.
Excellent. All right. What about if we had, see, we can have a go at something like this, I suppose. What about if we had something like this? Now, can you remember your transformations, your curve transformations?
Yeah, so is that things like f of x take 2 would be translation
Very good.
-2.
Absolutely. Absolutely spot on. You're absolutely spot on. So how do we do something like this now?
Could you find, so is it the natural log of 4x plus 1 squared and then move it down by 2?
You're going to move it down by 2. Yep, absolutely. But first, we've got to suss out what this looks like, haven't we?
Yeah.
We work what that looks like.
So if we've got the natural log of x is
So I'll let you have a go at it, and then once you think you are where you should be, but do keep talking out loud because it gives me an idea of what you're doing on paper, and then you can bring your final graph to the camera, and I shall look at it there in that way. Yeah, good.
So the 4x would mean scale factor of a quarter in the x scale.
Good, well done.
So then the +1 would mean it moves to the left. So then it would cross 0.
Very good.
And then if you move that down by 2, it would cross the y-axis at -2. And then kind of have a shape like this, but then I could find the turning point. Wait. No, wait. Could I find the turning point?
You could, but if you've got enough points, you might be able to figure out where that turning point might be.
Oh, but yeah, so then it's squared. So would
so the fact that it's squared is giving a bit of a hint then in terms of the fact
there's
that
nothing in the negative.
Very good. There will be no values of y that are negative. Very good.
So then it would kind of give like a it kind of give a x squared graph, kind of.
Kind of. Very good. Very good. Very good. And have you got your final shape?
Yeah. Would it be something like this?
Let me have a look. I'm just going to blow your picture up to a slightly bigger. You're nearly there. You're nearly there. You're absolutely nearly there. And we can look at this in, yeah, you're so nearly there in terms of general shape. Yeah. And of course, if they're looking for a sketch, sometimes they will be very specific with they want you to identify all the points, but generally getting the right general shape of what it looks ish counts towards you demonstrating that you have an idea of how to go about these things. So if we just almost break it down a little bit, we know that this is going to somewhat be related to the natural log of x function, isn't it? Because it's got a natural log in there. So we could start off with that as little key steps just to kind of break the problem down a little bit. So we know that if I was to plot y equals natural log of x, which you rightly plotted correctly, it looks something like this, where this coordinate there is 1. Yeah. What about now if we wanted to plot something which was y equals natural log of x plus 1? Yeah.
Yeah.
The good thing about starting with this is that we can slowly start moving the coordinates and seeing what's happening. Okay. So there you go. That's my y, that's my x. Well, this means I've got to move my natural log x or shift it 1, isn't it? So here there's an asymptote. This here is what we call an asymptote because the graph never reaches that. So this asymptote will shift as well. What does it shift to? It shifts to the position of -1. So the new graph now is not going to cut through there. And this 1 here moves, shifts 1. So it's now at 0. So it's going to look like this.
Yeah.
Okay, it's not perfect graph, but kind of get the idea. Okay. Now if I change this to make it look to y equals natural log of 4x plus 1. Well, now what's this 4 term going to do? It's going to quarter the period, isn't it? Or quarter everything. So where this was -1, this now becomes -1/4. Good. So now we're at -1/4. And so it looks like, oops. And so it's something like this. Now we can start thinking about what would it look like if I used ln for x plus 1 squared. What's going to happen this time around? Well, all these values here, which are negative of y, are now going to be squared, aren't they? Does that make sense? All these values here are now going to be squared, so they're going to take a positive term. Okay, and all these values here as well are going to be squared, so it's going to take on something that looks like a squared type of graph. So what's this now combined going to look like? I'm just going to move the camera here. So all this combined will look something. Of course, I've still got my -1/4 there, but this will now look like this, which was kind of that shape you had. Yeah, but then I can then move this over to the other side, and now I have a -2. That makes sense? So now I have the graph of y equals, yeah. So this would mean shifting the graph down 2 units. So far, so good. And so I have something that has got an asymptote of -1/4, but now does this. And I can find these points here. And how am I going to find them? Well, I solve this equation here. Yeah, where now say the y becomes 0. So I get 0 plus 2 equals natural log 4x plus 1 squared. Yeah. And of course, then I need to find the square root of that. So √2 equals natural log of 4x plus 1. Okay. And then to find the values in here, well, what do I do then? Well, I know that, in other words, 4x plus 1 must be equal to, it's a square root, so there's 2 forms, isn't it? The plus and the minus. So now I get e to the minus √2, or we have 4x plus 1, which is equal to e to the positive √2. So far, so good. Which now gives me, and I can work out these values of x. So the first value of x, where y is 0, these 2 points, as it were, these are, by the way, let's just put this is 0 minus 2. So these 2 parts now become, I've got 4x equals -1 minus e to the -2. I'll divide by 4. So in other words, x equals to 1/4 of -1 minus e to the -2, or x equals to, I solve this equation here, which is e to the √2 minus 1. And of course, this is 1/4 again. Yeah. So this will correspond to that point, and that will correspond to the other point. So far, so good?
Yeah.
Good. Okay, another one for you to try, which again is worth, so we're not quite in. How do you sketch a graph of something like this?
If I'm looking at the where it crosses the the x-axis, then I put y equal to 0, and then log x2. So then it would be so then I could say x to the 0. That's weird. Because then you get x to the 0 equals 2, which wouldn't work. So then if I think what happens as x gets bigger, as x gets, so if it was 4, it would be half. So as x gets bigger, would y get smaller?
So as x gets bigger,
yeah.
So that would be the base we're using there, wouldn't it?
Yeah.
So that's to the base. Now that one will pose some challenges, just as a way of giving you a bit of a hint to this. On its own as it is, it's not user-friendly as a function, because we're now using x as the base itself. So it'd be worth changing this so that we can actually work with a base that we know. At the moment, the base is an unknown. So do you remember in your core 2 maths doing base changes? Do you know how to do a base change?
No.
Okay. So you have learned logs, yes, though?
Yeah.
Good. So you probably remember it when I write it like this. So if you're given log a, log of b to base a, you can do a log change, okay, to a new log.
Okay.
Say log to the base of c. So this is the same as log to the base of c over log to the base of c of a. Okay.
Right. Okay.
So this is look in your notes. I'm fairly certain because I'm fairly certain that this is one you'd have encountered possibly towards the later end of year 12. I'm hoping you'd have seen this when you learned logs, because that have shortchanged you otherwise if they didn't tell you. This is something the interviewers will be expecting you to know, okay? But anyway, that's the whole point of these sessions, is to reintroduce them so you go there a lot more prepared. So the other way, a special case to think about this is we can make this C to be base B.
Right, okay.
Now can you see what happens? Well, what is log of B to the base B? That is just 1.
Yeah.
So I've changed the log. So this now, log to the base, log in base A of B is the same as 1 over log in base B of A. Okay?
Right, okay.
So the next thing we do now with this key fact is we change this using the same law that we've just learned here. So this then becomes, in other words, log to base x of 2 is the same as log to the base 2 of 2 and log to the base 2 of x. So this becomes as 1 over log to the base 2 of x. This is much easier to work with than that.
Right. Okay.
That make sense?
Yeah.
Good. So how might we proceed from here now that we have an alternative representation that is much more livable with?
So then, sorry if I just rewrite it. So y equals 1 over log 2x. So then if I plot y equals so if I plot y equals log 2x, and then it would be
Very good, and
log,
that's a very good starting point, Alfie. So where you've thought about, well, what would log to the base 2 of x be? Let me try and work out what would this thing look like. When you work out what this thing looks like, it starts opening up your eyes as to what 1 over this thing might turn out to be. Yeah, very good. So for y equals log to the base 2 of x, hopefully you remember that this would be a reflection of y equals 2 to the power of x in the line y equals to x. So that's my line, y equals to x. So hopefully your curve should look like this.
Yeah.
Where this would be 1, 0, the coordinate of that point. Yeah?
Yeah.
Well done. Excellent. Good. Now what are we going to do? Now we have to reciprocate. So if I had 1 over these values here, what might that look like?
So if it was so let's say that's so then it would be much smaller and closer to the x-axis. And then yeah, would everything move closer to the x-axis? So
to a degree, but what I want you to now spot here very importantly is at this point, which is the intercept, we know this is the graph of log of base 2 to the x. Yeah. The y value here is 0.
Yeah.
So when you go into this equation now, which is 1 over log to the base 2 of x, remember this part here represents your y value in this curve.
Right. Okay.
So where the y is 0, we know that again, this will be indeterminate. That makes sense?
Yeah.
So in which case, if I have my graph like so, I know just with more practice, your eyes will begin to start seeing some of these things, of course. So it means that where my x is 1, my y, which is in my function, will be 0. So that must be an asymptote. So there must be an asymptote at this point in my actual graph, if you can relate to that. And now you can also see something as well. Yeah, as the values of y become very big and you put them into this function, the value in the second function of y are going to become very small. Yeah,
Yeah.
because we're now dividing by very huge. So we know that it's going to tend that way, getting smaller. But as they become very much smaller, in the other function, which is the reciprocal, they're going to increase. So it's now going to look something like this. But hang on, we've now got this point here as well, this other side, on the other side of the coordinate where we've got 1, the asymptote. So what about these points? They'll do the same thing as well, won't they? So as this becomes or tends towards infinity, because that's what would happen here, then I'm dividing 1 divided by infinity. So this tends to 0. Does that make sense?
Yeah.
Because we're looking at this function and doing 1 divided by all the y terms in this function. So it's then going to look like this. And there'll be another asymptote.
Right. Okay.
Yeah.
Yeah.
Much trickier, but what again I'm happy is that it's revealed this base change trick. Right. And even just for your A levels as well, the examiner absolutely loves this one because they know that students forget about it.
Yeah.
Yeah. So yeah. Hint, hint, whenever something is logged to a variable, remove that variable if you've got a number next to it.
Yeah.
Okay. So that's one way of looking at these. Okay. There's quite a lot of questions in here, Alfie. But I'm glad that we went at the pace we went at so that we could, you could actually assimilate and absorb what's going on. There's each of these questions has got its own tricks and a few things. I'm just kind of panning through some of these here, just to kind of give you a bit of an idea of how to go about thinking about these problems. Now, of course, it's a bit of a shame that we haven't had enough days, but it is what it is, and we'll just have to work with the time we've got. How have you found today anyway?
Yeah, I found it good.
Good?
Yeah.
Good stuff.
But some of the things such as the base change, because I went over everything that we did. I went through all the booklets that I got last year, and
okay,
it wasn't in there. So
which examining board are you within for maths?
I'm with AQA.
AQA.
Yeah.
Okay, we are at my school. We are with AQA.
Yeah.
And it was in the spec for AQA. So if you go onto the log section of your mathematical spec.
Yeah.
Yeah, have you got that open?
I'll go to it now.
Yeah. And if you just share your screen with me, I'll might help you identify it.
Right. So. Is it this one?
Yeah, that's it. So if we just go to the log section, vectors, coordinate geometry, exponentials and logs. Yeah, there we go, page 17. Okay, so no and content, there we go. So there we go. Understand use of law of logs. Okay, select the base A, that. Okay, let's have a look here, including, we've got that one. Okay, if we scroll further down, use logarithmic, understand, hang on, solve equations of the form. Scroll up again, let me have a look again at, no one uses a definition of log. Yeah, that's fine. No one uses natural log. That's fine. Understand. So where have they hidden it then? That's there. Right. I'm very, very surprised then that. So must that be in C2 then? It's definitely part of the A-level spec, that I can guarantee you without a shadow of a doubt.
Yeah.
I'm
I think it is.
absolutely certain.
Yeah.
Understand and use the laws of logarithms, including because every examining board and generally, if you like, Ofqual will give all the examining boards what material has to go in there. The sequence of how they do it is down to the examining board themselves. But I'm surprised it's not explicit. I'd have thought it should be explicit. And you've got a textbook there, Alfie, by any chance?
Yeah.
Yeah. Do you just want to go through your logarithm section in the textbook and check it?
So I can see the normal laws
Yeah.
of logs, and then there's reduction to linear form. I can't see it in the.
Anything in there, Alfie?
No, I can't see anything. No.
I'm absolutely surprised that is not included in there. It's a general part. Okay, so that's another one I can look at because this has got right. So
In our school, what they do is they give us like their school version of the textbook, so
yeah,
so that we can follow along. And in that, they've only got the 3 logs, so the one.
okay, the ones that we
the
saw in the spec, is that right?
Yeah, only they
Right.
were included.
So I'm just looking here to see. I'm just going to the AQA part. Just bear with me, Alfie. Okay, all right, there we go. And if we come over here, all right. I'm just looking through this very quickly. Okay. All right. Just have a look here. Okay, we've got that. We've got that. Okay. Oh, I see what I may have confused it with then. Right, okay. Okay. So what AQA have done, Alfie, My apologies on this one. They've got that in the further mat spec.
Right.
Okay.
Yeah.
Other examining boards have it in the normal spec. And that is
Right.
why I was confused, because I'm sure I know that they've done it, but that's the further mats group. So the core mats group don't go as far as that. But nonetheless, it's the only one remaining rule on logs that you are not told. Okay, but now that you know it, it's a nice little rule. And hopefully there's still going to be, I'm just trying to think if it might come in handy. Yeah, but at
Okay,
least you're
yeah.
exposed to it, so there's no harm at all. All right.
Yeah.
Now, the other thing I was going to say, of course, it's just because of the time. Did you want to have another session tomorrow, or how would you want it to be? Would you just want to work through these extra problems that I'll send to you?
I think if you send me the other ones, I'll have a look how I get
And
on.
then
And
see how you get on. Yeah, I think
yeah.
that might be a good idea.
Also, so have you been recording this session?
Yes, the whole of the video has been recorded.
So would it be okay if I have the video just so I could go over it?
Oh yeah, oh certainly. I recorded it so
Okay.
you could have the video. It is your video. I will not be
Okay.
keeping the video, so you'll get the video tonight in the next half an hour or so. I feel that's not a problem at all. And I'll also send you the board work and also the extra work that you can have a go at. And then just let me know, because I've got some appointments in the afternoon. So I've got some commitments really. So I won't be available sort of between the hours of about 2 and maybe about 6 o'clock.
Okay, that's fine.
Yeah. So just let me know anyway. Good stuff. All right. Well, keep up the good work, Alfie, and please let me know. And if for any reason I don't hear from you and you work through, okay, I definitely wish you all the best for your interview on Monday.
Thank you.
All right. You're most welcome.
Thank you. See you.
Cheers again, Alfie. Bye now.
Bye.
Bye.